Okay, I think we'll get started. So today we're going to talk about net ionic equations. This is going to be another short video because this material, the work really rests on you to practice and make sure that you understand this very well. It's a very important topic. There's not a lot to say, but it does tend to be something that trips up students that I've seen in my experience. So just make sure you're very comfortable with the idea. Practice some problems in whatever general chemistry book you have, and you should be good to go. All right, so first things first, this deals with electrolytes, and electrolytes are compounds that break up in particular in water. We're focusing primarily in water here now. So sodium chloride is an example of an electrolyte. The sodium chloride salt, as a compound, when you put it into water, will break up into sodium and chloride ions. Now, your book will have a solubility chart in it. Every general chemistry book will have one, regardless of which one you picked up. So spend some time looking at that. Try to get comfortable with what typical or what common salts or electrolytes are soluble and what are insoluble in water. There's some general rules of thumb. I don't think it's necessary to completely memorize the chart, but you do want to familiarize yourself with it a little bit. So once we have that, then you'll know when you mix a couple of ions together, will they form a so-called precipitate, and that's a precipitation reaction. And an example of that here is if we were to put sodium chloride into a beaker and we go check the solubility chart, we would see that it's soluble. If we put silver nitrate into a beaker, if we check our solubility chart in our book, we'll see that that too is soluble. So these two beakers, those salts would dissolve, or those electrolytes would dissolve. However, if we put them together, mix them together, it turns out that when we check our solubility chart, sodium nitrate is soluble, so that will remain still as sodium and nitrate, but silver chloride is insoluble, so that will come out as a solid solution at the bottom of the beaker. Now we add a nomenclature we add a notation to the typical reaction when we're talking about this type of thing. When we're talking about electrolytes in solution, we put the letters AQ for aqueous in parentheses by the particular compound. So in its sort of most elementary form, the reaction is written this way. And you can see the aqueous here. Now the sodium or the silver chloride, that's a solid, so that's written as S for solid. L is used for liquid and G for gas. Notice aqueous is not liquid, it means dissolved in water. We'll see an example over here where we actually make some water and that's a liquid. Or if we make some other type of liquid, that's a liquid as well. All right, so how can we use some of these ideas then to help simplify the understanding of the chemistry that's going on? We think about what are the conditions of each of the possible ions before and after the reaction. And so this is not what the sodium chloride is in this beaker. This is actually sodium ion and chloride ions separated or dissolved in the solution. Likewise, this is not silver nitrate in water. This is silver ion and nitrate ion in the water. After they've had a chance to react, the silver chloride is a single unit as a solid. So that has chemically changed. It's gone from silver ion to being part of this compound as a solid. And likewise, the chloride has changed. It was a lone ion. Now it is a part of the solid. But the sodium ion is still just a sodium ion. So chemically, the sodium ion has not experienced any change. So it's not an essential part of the chemical reaction. And likewise, the nitrate. Now, of course, they had to be there to be these salts in the first place, but in terms of the direct chemistry that's happening and captured in this reaction, these are so-called spectator ions. They don't participate in the chemistry. And so what we can do is we can treat this much like a mathematical equation and cancel the spectator ions, leaving just the essential chemistry, which is called the net ionic equation. So if we cancel the ions that are the same before and after the reaction, then we are left with simply the so-called net ionic equation. And so the net ionic equation captures that essential chemistry of what's happening in the beaker. All right, well, let's do a couple more examples. Let's look at an acid-base reaction here. So very typical acid-base, sodium hydroxide with hydrochloric acid. Well, both sodium hydroxide is a strong base. So that means by strong base, it means it completely breaks up in water. So we would have a sodium plus aqueous and a OH minus aqueous. And then likewise, hydrochloric acid is a strong acid. So we would have a H plus and a Cl minus aqueous. And then sodium chloride is a strong salt, strong electrolyte, so that stays broken up. But H plus and OH minus will largely form water. There's a little bit of OH minus and H plus left, but largely it'll form water. So if there's any excess of this around, it will mostly form water, and water is a liquid. And we don't say water aqueous here, it's a liquid. Oh, I did say aqueous here. Water liquid here. Okay. And so let's write the net ionic equation. Well, the sodium cancels and the chloride cancels. They're spectator ions. And notice the difference here. Chlorine was not a spectator ion over here. It is a spectator ion over here. So whether something, you don't classify an ion as being a spectator ion. It has to be within the context of the particular reaction. So in this reaction, chlorine is playing the role of a spectator ion. And so then our net ionic equation, right, loses any identity of the particular acid or base. Now, well, let's do one more example of a diprotic acid. Here we have sulfuric acid, and we'll let that completely break up into two H pluses and SO4 2 minus a sulfate ion in aqueous. Likewise, sodium and hydroxide. We've got the stoichiometry such that the equation is balanced. You want to do that ahead of time. And then we can identify the sodium sulfate as being a strong electrolyte, so that will break up. And then we are going to create two waters. The net ionic equation then, the sulfates are spectator ions, the sodiums are spectator ions, and we're left with 2H plus to 2OH minus goes to 2H2O, and this is liquid again. Now, we know that we can multiply the stoichiometry by any number, any common value. So let's multiply this by 1/2, and we get this. And notice this is the same as we got over here. And this will be true for any electrolytic acid or base. So we can, the most simple definition of an acid would be an electrolyte in which the cation is H plus. And then the simplest definition of a base would be an electrolytic base in which the anion is OH minus. In that setting, we will always have the same net ionic equation. Now, it might come out that they're multiplied by some overall stoichiometric factor, but that's okay. Now, that is a very restricted and important, but a restricted definition of acid and base. We will see progressively more definition, higher definitions of acid and bases. We go from what's called the electrolytic acid to a Bronsted acid base to finally a Lewis acid base. But essentially an acid is anything that ultimately raises the concentration of H+ in water. So this is always talking in water now, acids and bases. A big area of chemistry is understanding acids in other solvents, but for us we're worried only about water. And then a base is anything that raises the OH minus concentration. Now, we haven't talked about this yet, but there's a relationship here between, well, I guess we've kind of talked about it. There's a relationship between if we raise the OH minus, then we have to reduce the H+, and vice versa if we're talking about water. All right, and then one final thing that isn't so much directly related to this, but because hydrogen is an ion in these settings a lot, it's reasonable to talk about it now, and that is, if we look at H+, this is completely unique in that it does not have any electrons. So it's just a bare proton. And if we think about our benchmarks for sizes, the hydrogen with its electron is about half an angstrom, and then without its electron, it's only the nucleus, which is about a Fermi, so 10 to the minus 15 meters. And so this is a very localized charge, which nature does not like. Nature doesn't like localized charges, and so we don't actually find a bare proton, except perhaps fleetingly in the water, but it's almost always globbed onto either 1, 2, 3, 4, etc. Water. So we never actually see H+, we see H3, O+, H5, O2 plus, and so on. And what's happening here is, let's say we've got now this hydrogen attached. This delocalizes that charge across this whole molecule. And then, of course, these are easy to make and break, and so this can come over here and get sort of passed around very easily through the hydrogen bonding network. And so the hydrogen ion behaves differently than any other ion in water, and as an acid, in the context of acids and bases, then the acid is actually this. Now it turns out that this is very convenient, and you're always going to still get things right if you do your paperwork or your the equations where you use H+. Because there's always water in the solution if we've got aqueous, which again we're always talking about aqueous for now, then if you just write H+, you'll be fine, and all the bookkeeping will turn out okay when you do net ionic equations. And actually a little more awkward to include this, because you have to pull a water that isn't from the any of the reactants, it's from the actual surrounding water. All right, so that's it for net ionic equations. Again, this is a little sneaky. It's a little bit harder than it seems. So if you followed along really well, that's great. So challenge yourself now. See if you can solve some of the problems in your book.